let's get back to this. So how do we check for the saturation dosage? There are methodologies that can be done in the lab, not just in your research and development laboratories, but also site labs, because these are very simple methodologies. This is an EN approach, Euronorm 447, where they describe this Marsh cone, which was derived from an initial test that people used to do for grouts. Okay. So when we use grouts, which have to be flowable, you have to establish that flowability by checking the time that the grout takes to flow out of a conical flask, conical setup. Now here, instead of the grout, we are using cement paste, where you are going on adding additional superplasticizer dosage. So let's say we choose let's say you are going to work with a concrete where the design calls for a water to cement ratio of 0.4. So you make cement paste with the same water cement ratio, 0.4, and you keep on adding superplasticizer to this paste and check the flow. So you fill up this cone with about 1 liter of the cement paste, and you stop the orifice at the bottom. After the entire thing is filled up, you remove your finger from the orifice and let the paste basically flow out. You have a measuring cylinder which is placed at the bottom. You check the time taken for 500 ml flow to happen. Okay, that is a typical procedure that is done for Marsh cone. You have 1 liter and you check the time taken for 500 ml flow or 500 ml of flow to happen from the orifice. The orifice size has to be fixed whether you are testing a cement paste or a mortar. For cement paste, typically we use 8 millimeter orifice. For mortars, we use about 12 millimeters orifice. So again, please try to see whether you can get your hands on this code, go through it in more detail and try to understand. It's a very simple test. It can be done anywhere. So all you need is this cone, which can be fabricated by any workshop, and then you need a stopwatch and you need some sort of a mixing apparatus to mix your paste. Right. So as you increase the superplasticizer dosage, the flow time keeps reducing, obviously, because material flows out much faster. So beyond a certain point, you are not seeing a major decline in the flow time. That means you are reaching saturation. You can do the same thing with the flow table spread also, no problem. You can do the same with the flow table spread, but only thing is there you need to probably have a flow table spread also includes the use of sand along with it. And otherwise you can use a mini flow spread, which is called the Mini-Slump cone, in which case the top diameter is 10 mm, bottom diameter is 20, top diameter is 20, bottom is 40 and the height is 60. What is your typical slump cone for concrete?
10, 20, 30
centimeters, yeah, 10 top, 20 at the bottom and 30 centimeters is the height of a typical slump cone for concrete. Now the ratio of the dimensions is the same here. We have 20 mm at the top, 40 mm at the bottom and 60 mm height. So this is a mini slump cone which could also be used to determine the saturation dosage. So as you can imagine, as the SP dosage increases, the spread which is seen in the slump cone increases, but beyond a particular point you will not see a major increase in the spread. So that is your saturation dosage. Now we talked about a case earlier where the superplasticizer molecule does not have any affinity for the cement at all, right. In such cases what will happen? As you add more and more admixture, you will not reach saturation, right. So you may have a condition where this curve keeps going down completely. So that is an incompatible combination. In some other cases what may happen is you added too much admixture, so bleeding starts happening. The water from your paste starts getting separated, and because of that, since water is lighter, the water will come up on the top, so you will have like thick paste at the bottom. So what will happen to the flow time? It may start going up, flow time may go up again. Why? Because the paste is now falling in chunks, it does not have the flowability because the water has separated out. Okay. So you need to evaluate this test carefully. It is a simple test. You do not need to make concrete. Once your design is ready, to understand the compatibility between your cement and chemical admixture, this test can be easily done at the job site. Okay. We will come back to this when we talk about some relative performance levels of different admixtures, but this is how you determine saturation dosage. Okay. So, again just to define it once more, saturation dosage is the minimum extent of dosage required to produce workable concrete, okay, to induce flowability in cement paste, to induce the maximum potential of flowability in cement paste, assuming that adsorption is the sole cause of flowability. So, what will happen if you increase temperature? What will happen to the saturation dosage when you increase temperature? It will come down. Why? Will it come down or go up? Why will it come down? That means you need less admixture to adsorb. Why? What will temperature do to the adsorption rate? Increase, no? So, you probably are going to end up adsorbing more SP onto the cement, but your workability, initial workability may improve at higher temperatures, but that is like counterintuitive. No? We always think that at high temperatures we are not able to maintain workability. It is not true. We are not able to maintain workability over a longer time. Workability retention will be a problem at high temperatures. Attainment of initial workability will not be a problem. Okay. So, again we will come back to that, those effects we will discuss in more detail. So, as I talked about, there is competitive adsorption also that may happen in the systems. Okay. Superplasticizer molecules, which I said are charged, get competition from other anionic species in solution for the adsorption sites, leading to incompatibility. Why does it lead to incompatibility? Because let us say sulfate, right? Why is sulfate needed in cement, or why is gypsum needed in cement? To slow down the reaction of aluminate, right? To slow down the reaction of aluminate, to have a much more controlled setting process. In the absence of gypsum, aluminate will react with water and produce flash setting, right? So, without gypsum that is what happens, but with gypsum the sulfate has to come to the surface of the aluminate and start reacting and prevent it from flash setting. Now, imagine an admixture like a sulfonate, lignosulfonate, naphthalene sulfonate, melamine sulfonate, right? Sulfate, sulfonate, same charge, negative charge, aluminate, positive charge. So, what will happen now? Instead of the sulfate from the cement that you want to come to the aluminate, you may have sulfonate from the admixture that comes to the aluminate. So, there is some competitive adsorption. Okay. The other way, the preferential adsorption of superplasticizers on aluminates at the expense of sulfate may cause issues with normal setting. So, there are two aspects here. Incompatibility here means you are losing effectiveness of the admixture to provide workability, because your admixture is simply getting adsorbed onto the aluminate and you do not have enough to adsorb on the other species. Okay. But since this admixture has now not permitted your sulfate to go and interact with the aluminate, your normal setting process is going to get affected. So, here this is an interesting process. You are getting loss of workability, but you are also getting delay in setting. Just imagine, these are counterintuitive. We expect that when setting happens we lose workability, but here you may end up having both problems. There is loss of workability because admixture effectiveness is going down, and since you have not permitted sulfate to interact with the C3A, your normal setting process is also going to get affected. Okay. So, you have to be very careful when you use lignosulfonates or naphthalene sulfonates. Polycarboxylates do not have the same problem, because there, as we will see later, the mechanism is not by this surface repulsion, electrostatic repulsion, it is more by the size of the molecule itself, we will see that. Okay. So, competitive adsorption has to be looked at carefully, and these days, right, just like when you make biryani you add several masalas, these days when we make special concretes we add several admixtures. You can have water reducer, you can have VMA, you can have shrinkage reducer. Now, all of these chemicals, many of them still work with the adsorption. They have to first adsorb and then lead to the effectiveness. and because of that there is again competition between the admixtures. So, how do you resolve this problem? What can you do to resolve this problem? So, here your challenge is to get the sulphate from the cement available to react with the C3A before your adsorption by the polymer happens. Can you do this? How can you do it? You can delay the time of addition of superplasticizer. You add the water to the cement first, let this initial dissolution take place. But there is another problem there. What if the gypsum that you use in your system does not dissolve fast? Right? So, that is another issue. So, again this is something we will talk about in more detail, the compatibility issues we will talk about in more detail. So, the first mechanism of producing this workability is electrostatic repulsion. As we discussed, many polymers like lignosulfonates, naphthene sulfonates, they have negative surface charge. As they wrap themselves around the cement particle, they give an overall negative zeta potential. Okay. So, there is lowering of the zeta potential that happens for the cement particle surface. Okay. So, people have actually measured this, about -30 to -50 millivolts have been reported for certain linear superplasticizer molecules. Okay. So, essentially what is causing the separation of cement particles is this layer formation on the top, charged layer formation, which leads to this double layer on the surface of adjacent particles, which causes osmotic force that resists the approach of the charged particles. Essentially, like charges repel, right, to put in simple terms. So, negatively charged cement particle surfaces are going apart from each other, and this, as I said, you typically see in your sulfonates, which give this negative charge onto your surface. Okay. So, surface electrostatic repulsion, it happens after adsorption. So, the steps are, first is adsorption, then your lowering of zeta potential, and then your electrostatic repulsion. Okay. Now, the same adsorption phenomenon also happens for the other types of molecules like polycarboxylates or vinyl copolymers. Those are also getting adsorbed onto the cement particles, but they are producing repulsion through this steric hindrance or steric repulsion. What is steric? Steric means related to the structure of the molecule. So, you have this polymer chain that is getting adsorbed onto the cement, but you have these side chains that are so bulky, right, that they are preventing particles from coming together. So, even here adsorption happens, but beyond that you have steric repulsion. So, bulkiness of the side chain, we saw the polymer structures in the last class, right, where polyethylene oxide, you have multiple units of that in the side chain, right. So, when you make these bulky side chains, it prevents the coming together of the particles, and that is called steric repulsion. Now, the charged system, the electrostatic repulsion based admixtures, the charge will diminish as the cement starts hydrating. Okay. As a result, you may not get effectiveness for a longer time, but with steric repulsion you get that effectiveness for a longer time because it does not rely on the surface charge. Okay. It does not rely on your maintenance of surface charge for a long period of time. Now, because of this interesting formulation of the polycarboxylic ether molecules, you can actually make different types of molecules to get different types of performance. So, let us say you want low dispersibility and short dispersibility retention. Can you give me some example of an application where you want less workability and less retention of workability? Any example of a concrete which needs to be applied with less workability and less retention of the workability? Pavement, yeah, concrete pavement, right. Concrete pavements, you do not need too much workability. At the same time, if it is workable for a longer time, then you are not gaining your strength fast enough, right. So, in this case, you go with a backbone polymer that is long, so that adsorption really happens, but then side chain length is short, so you do not really get too much repulsion, okay. And you have a large number of side chains which go and attract themselves to the surface, adsorb themselves on the surface, and you do not really get a retention of this workability for a long period of time. You want high dispersibility, let us say self compacting concrete. In such cases, your backbone polymer may be short, but your side chain length has to be quite long to provide you the excessive workability. And of course, when you want retention of the same thing, you still have to go with short and long, but a large number of side chains to provide you that effectiveness for a longer period of time. So, what I am trying to say here is, I mean, these combinations may not work out all the time, but what I am trying to say here is you can now play around with the molecule and control the length of these side chains, control the length of the main polymer chain to acquire specific polymers that work for your particular application. So, because of PCEs, now we can actually engineer the superplasticizer for any application, like for 3D printing, like for self-compacting concrete, right, for all of these, for slip forming. So, you can actually now start looking at functionalities being brought in. The side chains need not just provide dispersibility, the side chains can also have some functional groups that can lead to other things. Like I said earlier, we have superplasticizers and VMA added separately. Now, side chain itself could have molecules that lead to the viscosity modification also. So, all of these aspects can now be brought in. So, in other words, we can make the admixture multi-functional, and that is the main advantage of PCEs. So, although they are expensive, the multifunctionality helps you reduce the extent of other chemicals that are needed for producing various different effects in your special concretes. Okay, at least this aspect we should talk about. In construction projects, everything finally boils down to cost. Okay, even just like in mileage of cars, we always say, right, kitna deti hai, right? Similarly, kitne mein aati hai? That's what everybody asks, right? You give the new product, how much does it cost? That's what the first question anybody asks you is. But the cost is not an absolute term, it's a relative term, so we have to pay attention to what we are talking about. So, let us say we have lignosulfonate, it's inexpensive, it's a first generation admixture, it's available typically as a water reducer, we simply use it at a higher dosage. But the problem is when you start using as SP as superplasticizer, there is inconsistency in the performance, right? More variation in properties, it retards, it entrains air, so there is a lot of problems. So, we won't even consider it for comparison of the costs and performance. But let us look at a case where we can modify the lignosulfonate. Now, we are causing retardation, and I talked about the fact that in lignosulfonate molecule there may be some sugars present that can cause retardation. Let us say you do some fermentation and remove the sugars, and we said that there is air entrainment present. Let us say you modify the formulation in such a way that the air entraining molecules are removed. We will talk about that later. So, when you do that, you can create what is called a modified lignosulfonate. There you can have controlled retardation and reduced air entrainment. Now, problem with this again is the lignosulfonate has its own limitations in working with extremely low water cement ratios. So, you cannot even imagine it being used for water cement ratios less than 0.4. Okay. Now, let us say the relative cost of the dry polymer is 20 rupees or 20 units, arbitrary units, 20 units. Okay. So, if you take a typical liquid that is available in the commercial sense, most liquids that are available for admixtures are either a 30% or a 40% solution. That means active ingredients are about 40%, remaining is just water. Okay. So, it is important because if you sell it as a liquid, it is easier to disperse in concrete mixtures. If you sell it as a powder, you need to take all that additional precautions. Okay. So, and most of these admixtures are sold as liquids. So, 8, let us say for a 40% solid solution, let us say the cost becomes 8 now. For a 150 millimeter slump in concrete, we may require around 4 kilograms per cubic meter of the modified lignosulfonate. That means our cost becomes now 4 into 8, that is 32 rupees per cubic meter for using modified lignosulfonate. You come to polynaphthalene sulfonate, it works well in conditions which we have in India, it is very good for warm climates. Okay. It has a cost which is not as high as polycarboxylates, but then again when you go with very low water cement ratios of less than 0.35, it is not very good. Some cases it can also lead to air entrainment, especially if the polynaphthalene sulfonate molecules do not have too many, do not have an adequate chain length. If you have a dimer or a trimer present, it will act like a surfactant, like your detergent, and produce more and more air in the system. Okay. So, here the relative cost of the dry polymer is higher, 40 rupees let us say, Again, for a 40% solution, you get 16 rupees as the cost. You do not need as much to produce the 150 millimeter workability. Okay. So, if you multiply the two, you get the cost to the concrete to be about 44 rupees or 45 rupees. Similarly, polymelamine sulfonate, problem is it does not work well in cold climates at all. It is very good for initial workability, it produces excellent concrete, it is an ideal concrete for precast conditions, but it does not retain workability long enough, no slump retention. It also cannot work at very low water cement ratio, so you can't really imagine it being used for very high strength concretes. Okay. The cost is higher, about 80 rupees, let us say, for the dry polymer, or 32 rupees for a 40% solid solution. Okay. So, that means again, let us say you need 2.8 kilogram per cubic meter to produce 150 mm slump, nearly the same as SNF. So, your overall cost is quite high now, 89.6 rupees. Polycarboxylate, we talked about the fact that it works extremely well. It is the material, it is the admixture of choice when we want to make high strength concrete, even as low as 0.15, which we will talk about later. Ultra high strength concrete can be prepared, right. In such cases, polycarboxylate is the only way to go. Some issues of retardation can happen at very low water cement ratios when you add too much dosage, that is obvious. Cost is going to be high, let us say 100 rupees. Now, typically these are sold at about 33% solids. Okay. So, let us say 30% solid, so you have 30 rupees as the cost of the solution. You need less dosage to acquire the same level of slump, because we want to produce 150 mm slump only, it is not a major demand in terms of workability. So, actually if you look at it, your cost contribution to concrete is only 48 rupees, which is only slightly higher than your sulfonated naphthalene formaldehyde. It is lower than melamine formaldehyde, it is higher than modified lignosulfonate, no doubt. But let us say you want to choose a concrete where we want to produce 200 mm slump, you may not even be able to make it with modified lignosulfonate, you can only do it with polycarboxylate or SNF. In such cases, your contribution of the cost to the concrete is what matters to produce concrete of a given effectiveness. It is not the unit cost of the material, but how much it actually costs for the concrete to achieve that level of performance. So, we have to change the way in which we look at the cost. The cost to achieve performance is what we desire. Okay. Like a Mercedes and an Ambassador are very different in initial cost, but if you think about maintenance in the long period of time, maintenance for an Ambassador, many of you probably do not even know what an Ambassador is, okay. You do not get to see any more in the streets, right. So, you have to spend a lot more for maintenance to get it running, to keep it running for a long period of time. Mercedes does not, but of course, when you do have to spend on maintenance on a Mercedes, you are done. But so that example does not totally apply to this condition, okay, because there is no maintenance here, right. I think we finished this segment. There is a lot of references are provided here, because these are of course the first one is the book that we are referring to quite often. The others are papers which you can actually access from our library network, and for those who need a little bit additional information, you can always go through these papers. Okay. Thank you.